5, 6. Obviously, they won't satisfy that all these minors are positive. All these ordered minors are positive. What does it take for all the ordered minors to be positive? What you need is for this picture of the x's to give you a convex polygon. Okay, and why is that? Well, you see, what is the determinant? What is this determinant? 1xa, 1xb, 1xc. That is just what you learned in junior high school as the area of the triangle with vertices A, B, and C. Right? That's the area of the triangle with vertices A, B, and C, but it's a signed area. Okay? So in order for all these areas to be positive, this polygon has got to be convex. All the areas to be oriented the same way, the polygon's got to be convex. So we have a simple picture that we can think of positive G3n as being in one-to-one correspondence with a set of all convex polygons that live in the plane. Okay? Just the moduli space of all convex polygons that live in the plane. But now you see why it's so much more interesting. You see, in the case of a simplex, if I want to go to the boundaries of a simplex, going to a boundary means you set some of these positivities, you make them equal to 0. You make things non-negative. You allow the closure. You allow some of them to be 0. But in the simplex, you can set anybody to 0 that you like. And then just go to a lower dimensional simplex. So you start with a tetrahedron, you go to triangles on the boundaries, and so on. However, in the Grassmannian, positive Grassmannian, it's different because I can't willy-nilly set any minor that I like to 0. Okay? And we can see why here. So let's say I take this picture. 1, 2, 3, 4, 5, 6. Let's say I take this picture and I want to make the minor 1, 3, 5 goes to 0. Okay? So remember, being positive means that all these minors are positive. So let's say I choose one of them, this one, 1, 3, 5, and I want to send that to 0. What does sending the minor 1, 3, 5 to 0 mean? It means that I'm making 1, 3, and 5 collinear with each other. So let's try to do that. Let me try to take 3 and move it so that it lies on the line 1, 5. Well, I can't do it. Before it gets there, 3 is going to lie on this line. And then I can't keep going anymore without changing the fact that it's convex. Okay? So you see that even though we didn't say so ahead of time, we just defined things with all the minors being positive, that the boundaries are already interesting. The boundaries involve consecutive guys becoming collinear. And then past that point, well, other things can happen. You can make this guy collinear, or you can take this guy who's there already and make it sit on top of 2 or sit on top of 4 and so on. But it's a much more intricate space of possibilities. Okay? And indeed, this was part of the story with the many-author paper from many years ago. The boundary structure of the positive Grassmannian is so rich as to be in one-to-one correspondence with every possible on-shell scattering process in n equals 4 super Yang mills. Okay. So, okay. And in a sense, all the different ways of expressing amplitudes with on-shell diagrams are picking pieces on the boundaries of the positive Grassmannian and saying, let's add these pieces up together to get the amplitude. Just like we saw in the easiest case for NMHV, we have to add up 1 I plus 1 J plus 1. Those pieces to get the amplitude. And that was the problem, because while each individual piece made perfect sense, each individual piece was an on-shell process, we didn't have an a priori reason, other than the desire to get the right answer from physics, other than the desire to make the answer local and unitary, to put the objects together in the particular way we're putting them together. So the amplitudron is the answer to the question, what is the question to which the amplitude is the answer? And so to do that, we need a second generalization. So triangle, the positive Grassmannian is the first generalization. But the second generalization starts by going from a triangle already to the inside of a convex polygon. So let's say I have some external data, again, and they're giving me a convex polygon. Now how do I talk about all the points on the inside of the convex polygon? Well, if I want to mimic what I did before, it's exactly the same thing. I say that the y's are C1, Z1 plus C6, Z6. And again, these C1 through C6 on GL1, and all the CA's are positive. Okay. Now this is a little bit, now, there's something else that I have to make sure of though, is that I want to make sure that this is indeed a convex polygon. So in order for this picture to make sense, I also have to assume that the z's, the coordinates here giving the that the z's, the external data, are positive. These are two different positivities. The external data has got to be positive for the polygon to be convex. Having been given that, you keep the z's fixed and you scan over all possible c's. All possible c's which are positive. And that covers all possible y's that are on the inside of the polygon. Okay. So it should be clear this is a very redundant way of covering the inside of the polygon. The space of c's mod GL1, for example, in this case is 6 minus 1, 5-dimensional. Much larger than 2-dimensional, which is the space of the polygon itself. Okay, so this is a very redundant covering of the polygon. Now, we can cover it less redundantly by setting some of the c's to 0. In fact, if I set all but 3 of the c's to 0, so let's say I have C1, C3, and C5, then the image of that particular, and so doing that is going to a low-dimensional boundary of this little positive Grassmannian, this little G1n, and setting a bunch of the c's to 0. If I keep C1, C3, and C5, the image of that in the polygon is the inside of this triangle. Okay, so I can take the collection of all the 2-dimensional images, all the 2-dimensional cells of G1n. I can just take the collection of all of them. That'll cover the inside of the polygon. And the final, most interesting thing I could do is to take a certain collection of cells of G1n. By cells, I just mean things where I set a bunch of the c's to 0, which gives me a triangulation. Okay. So if I take the cells where only 1, I, and I plus 1 are non-vanishing, only these c's are non-vanishing, and the rest vanish, the image of one of those things is a triangle like this, and if I look at the collection of all of those triangles, I cover the inside of the polygon. So if no one ever told you about the polygon, if someone only told you about positive G1n, and said, here's a funny collection of cells, I like them, 1, I plus 1, they're great, take these collection, right? You would say, why the hell would I take that collection? I have no idea what's good about that particular collection. Only when someone tells you that you're supposed to look at the image, the C dot Z image, does it make sense? You say, aha, they're triangulating a space. Not in G1n, not inside the positive Grassmannian, but inside this external space. In fact, the space is just G13 in this case. The space of Y is just this 2-dimensional plane. Okay, so that's a generalization. Triangle to polygon. Now, right here, we can do something else. Right here, we can also associate with each triangle. See, inside any given triangle, in that triangle, I can write y as, let's say, ZA plus beta ZB plus gamma ZC. This is inside any given triangle. And it's natural to look at the form d beta over d beta, d gamma over gamma. Okay? This is a form that has logarithmic singularities by construction. It's a form that has logarithmic singularities on the boundaries of the triangle. Okay? And in fact, I can write it more invariantly. I can write this form as y dy, this is a little exercise, y dy dy, abc squared over yab, ybc, yca. nice positive, you put nice positive coordinates that cover the inside of the triangle. There is this form, which puts logarithmic singularities on the boundary of the triangle. And therefore, if you tile this space, by adding these forms, if you add the forms for a triangulation, you're going to get a form that has logarithmic singularities on the boundary of the whole space. Okay, so so given this polygon P, there's some form omega P that has, in this case, a 2 form. It has log singularities on the boundary of P. Now, in 15 minutes, I will talk about a different interpretation of this form, a slightly more familiar interpretation as an area. Okay, this is also the area of a triangle. What I just wrote down is the area of a triangle. But it's not the area of this triangle. It's not the area of the triangle ABC with some point Y sitting here. It's the area of a dual triangle. It's the area of, if I go to a space where I replace the points by lines, and Y, which is the point, becomes a line, then if I think about Y as the line at infinity, then that exact formula is the area of the affine triangle. Okay? That's the junior high school formula for the area of this triangle. But we'll get there. And this form it's a form of logarithmic singularities on the boundary of P, of the polygon, and is the area of the dual polygon. Okay? So that's where the first example of this duality, which is totally classic and familiar for polygons. You take a polygon, or any polytope in a projective space, and we can have the duality in which we interchange points and planes with each other. The claim is that there's a form that has logarithmic singularities on the boundary of P, and that form is equal to the volume of the dual of P. Okay. So in this case, it's perfectly well understood why this is the case. I won't have time to explain it today, but yeah, there's a lovely proof that one thing is equal to the other that just proceeds via Fourier transform. Okay? So it's a kind of a classic kind of duality from many points of view, an abelian simple duality. Okay? The dual amplituhedron that I'm talking about, but we don't yet know what it is trying to find some analog of this classical notion of dual for polytopes for the amplituhedron. Okay? But I haven't quite told you what the amplituhedron is yet, but that was just jumping ahead to where we're. Let me finish defining the amplituhedron. So, we generalize triangles to polygons, and now what we're going to do is we're going to generalize this into the Grassmannian in exactly the way that we've generalized triangles into the positive Grassmannian. The exact analog. So instead of having one Y, which was a combination of a bunch of Z's, I'm going to imagine, just to write it all in generality, that I have KYs. So alpha runs from 1 to K. But I only care about the K plane that lives in, I only care about the K plane made out of all of these guys. So I'm going to mod out by the GLK that acts on that index. This I is going to run from 1 to K plus something bigger than K. So I'll call it K plus M. M is going to have to end up being even for reasons I won't explain. And M equals 2 is the sort of simplest version of the amplituhedron. But M equals 4 is the, in a sense, minimal version that includes the idea of what allows us to define loops. And this is what we need for physics. Okay? You can talk about the amplitude for M equals 6, 8, and higher as well. What it corresponds to is some theories with a generalized notion of space-time and generalized notion of unitarity. There are funny theories where instead of factorizing when two things splitting in 2, the singularities of the amplitude happen splitting in 3. Okay, splitting in 4 and higher. Okay, so there are all such objects exist. They're Yangian invariant. They have all the same kind of symmetries. They're SL M/M generalization of what we're familiar with for ordinary amplitudes that have been studied not at all for perhaps obvious reasons, but they might play an interesting role in something someday. Anyway, M equals 4 is what we care about for physics. And so external data. So here's my z's. Okay? And I want to say that they're a positive combination of external data. Okay, so now the z's are going to be fixed. They're fixed, and they're going to be positive in the sense that all their ordered minors are positive. And the c's are going to be, they're going to live in positive GKN, in the sense that all of their ordered minors are positive. So that's it. If I put the little pluses here, that defines the space. Okay, so that's it. That's a subspace of GK, K plus M. Okay. The Y's are a subspace of GK, K plus M. The case of the polygon that we just talked about is K equals 1, N equals 2. Okay. And so that's what we call the tree amplitude. Okay, so that object. Now the claim is that if you find the form that has logarithmic singularities on the boundary of that object, that you found the amplitude. You found the tree amplitude. And in order to complete defining it, I have to tell you how you actually get an amplitude out of this thing. So far there's just geometry. And maybe with some work, there's geometry and some form. Okay, so there's some form that depends on y and depends on the z's. But how does this turn into an actual amplitude? Well, let me describe it geometrically first. So this y, let me put m equals 4 from the get-go. The y is a k-plane that lives in k plus 4 dimensions. So you imagine you have a sort of k by k plus 4 matrix. The y is a k-plane that lives in k plus 4 dimensions. Here's y. The z's are k plus 4 dimensional vectors. So that's weird, right? The data, the external data, is not 4-dimensional momentum twisters that we were talking about. The data is 4 plus k dimensional. Okay? So all the information about the helicity in k is being encoded in these extra k components of the z's. So this is 4 sitting up here, but that's the way to think about it. That the z has a piece that's 4-dimensional. They're the normal bosonic momentum twisters, and it has a form which lives in the 4 plus k dimensions. Okay? Now it's not completely obvious, but it turns out that this form has the property that you can Taylor expand it in the z's. And in fact, every term in the Taylor expansion has exactly 4k x's, has weight 4k in all the x's. This is not totally obvious, but it's related to the fact that these are somehow volumes, or the duals to volumes. Okay? But because they have weight 4k in all the x's, and only because of that, it's useful just to organize all of them to write each one of these x's as some phi times eta. Okay, 4 phi's, but then 1 for, so I have some C1 up to CK for each particle. So I write each C1 as phi 1, eta A, C2 as phi 2, eta A, okay, and so on. CK as phi K, eta A. The phi's are Grassmann, the etas are Grassmann, and there's 4 of each. I runs from 1 to 4. Okay? This I runs from 1 to 4. Now, we can write this form omega of y and z. This has the d4 times k y. Remember, it's a 4-plane in dimensions. Okay, so it's a k-plane. Sorry, the k-plane in k plus 4 dimensions. So there's a dk times k plus 4y mod glk. There's that piece multiplied by a function of omega. Multiplied by a function of the y and the z's. We can always use k by k linear transformations to bring y to the form, for example, which is 0 up here, and then just looks like 1, 0, 0, 0 up to 0, 0, 1 for this k by k block down here. So this is k by k plus 4. So this is exactly the basis in which each z is the bosonic momentum twistor z and these x's. And that defines exactly what I mean. Okay? It's the z's in the direction of the y's are these extra components. I'm just going through all this just so you see there's something that's just completely motivated from the geometry. You have a form, depends on y and z. There's a part of z in y, the part not in y. You make the part in y infinitesimal. Why? There's no other information in it because the form has weight 4k and these extra variables anyway. So this is just a convenient way to make a generating function out of all that information. But you see that the underlying object is bosonic. It's not fermionic. There's no supergeometry here. It's completely ordinary bosonic geometry. And then finally, you take d4 phi 1 up to d4 phi k of this function of y in Ca, and that is now literally the superamplitude, m and k of the bosonic guys and the a's. This depends on k. Everything here depends on n. Okay, so once you have this form, the form lives on the space of k-planes in k plus 4 dimensions. Okay? It's defined by having logarithmic singularities on the boundary of this space. Okay? Once you have that form, you have the amplitude. And in fact, in most of our work, we never talk about the amplitude ever again, because there's a lot to be learned in this completely bosonic y space. So we move around in this positive y space. Okay. So that's just for the tree amplituhedron. I think that if I'm going to talk about the dual at all, that I won't have time to tell you how the loop level amplituhedron is defined, but we'll have our hands full already, even just thinking about the dual at tree level. All right. Okay, so again, roughly, we're given external data z's. We're given the space of k-planes in k plus 4, the space of k-planes in k plus 4 dimensions. In that space, there's the inside of some region, which is defined by the z's. Okay? There's some canonical inside, which is defined by y is equal to c plus dot z plus, and then a form with log singularities on the boundary of the space, on the boundary of this amplituhedron, gives me the scattering. All right, so that's one description of the physics, and let me just spend 5 minutes to just tell you, for example, how this answers the question, some of the questions for where, for example, where locality and factorization come from. Let's just return to the simplest case, where k is still 1, so we're not even dealing with fancy case yet where we have determinants made out of these C's. But now m equals 4. Okay, so these Z's are 5-dimensional vectors. So I runs from 1 to 5. Okay? And they satisfy that these guys are all positive. Okay? So this is a 4-dimensional space. Okay? Looks at a 4-dimensional projection space. So where are the boundaries of this 4-dimensional space? Now here it's obviously very simple. It's all just flat boundaries. They're all just hyperplanes. So let's see if we can find where are the boundaries of this space. We can't visualize it like we could for the polygon. But let's just take a little bit of inspiration from the polygon for a second. Let's say that we couldn't visualize. How do I know, for example, that 1, 3, the line 1, 3, 1, 2, 3, how do I know that 1, 3 is not a boundary? I know that it's not a boundary because if I look at y, 1, 3, y, 1, 3, as I move around inside the polygon, can be either positive or negative, right? If y is in here, then y, 1, 3 is positive. If y is out there, then y, 1, 3 is negative. Whereas y, 1, 2 is always positive. Okay? Y, 2, 3 is always positive, and so on. Okay, so that's how you can discover where the boundaries are. You look for the boundaries for which y times that boundary is always positive. Okay? Well, let's try that in our case. Let's examine a generic boundary y, ZA, ZB, ZC, ZD. Okay? So, so this is the sum of CI, ZI, ZA, ZB, ZC, ZD. And these CIs are positive. So you see this has a chance to be positive because these Z's are positive, right? These Z's have to be positive if they're ordered properly, right? The trouble is, in general, they're not going to be ordered properly. And now I'm drawing something in index space. So here is index 1, index 2, 3, 4, 5. So if here's A, B, C, and D, then you see that if A, B, C, D are generic, there's no way this is always going to be positive. For example, one A, B, C, D will be positive, but if there's an index caught between A and B here, then that term will be negative, because I'll have to reorder. I'll have to reorder it in here to put it in increasing order. Okay? So if the indices A, B, C, and D are totally generic and spread around the circle, totally generic places, there's no way that sum is going to be positive. Sometimes it'll be positive, sometimes it'll be negative. There's only one case where it's guaranteed to always be positive, which is when this is of the form I plus 1, j plus 1. Okay, because when it's I plus 1, j plus 1, then no matter where you are, I plus 1, j plus 1, no matter where you are, you have to jump over 2 indices at a time in order to reorder it, and so it's always positive. Okay. So you see, that's quite magical. Without putting anything about no space-time interpretation, none of this stuff, all of a sudden, just positivity makes I plus 1, j plus 1 special. Right? It tells you that the boundaries of the space are exactly when y, I plus 1, j plus 1 goes to 0. Okay? Now, if you go back to thinking what that means in terms of the bosonic momentum twisters, remember I told you that you have to put y in the form, in this case 0, 0, 0, 1, and then each z is something up here and some c crap down here. So what does it mean when y, zi, zi plus 1, zj, zj plus 1 goes to 0? It precisely means that in terms of these little bosonic momentum twisters, they're precisely sitting on a factorization channel. Okay. So we discover that the boundaries of the amplitudehedron correspond precisely to factorization channels. Okay. Now, this much, another 10 minutes, and I could show you why, purely from the fact that these matrices have to have positive determinants, when you sit on the factorization